So next up, we're going to be talking about energy. We have Jonathan Keep and Aston Smith. I'll hand that to you. And Aston, I'll let you introduce the session.
Thank you. Oh, we're working, which was a good start. Good morning, everybody. I have the really easy job of just introducing John Keep from UK IFS. I don't want to spoil the presentation, so I'll keep it nice and short. So Dassault and UK IFS have been working together for the past 2.5 years. And really, we are embracing that real partnership approach for this incredible program. Now, what we're doing is we are helping develop the people, processes, and tools, and making sure that every decision that we make as a team is absolutely best for program. So, John, if I don't mind. Well, when I asked casually to John a few weeks ago, would you mind talking at this event? He jumped at the chance, so he could really tell everybody here the story so far. So please, John, take it away.
Good morning. So fusion is the source of power, the process that powers all of our stars. The sun is actually our ultimate source of all of our energy. Fusion is a process where we take small atoms and they combine together to form larger atoms. And in that process, they release a little bit of energy. STEP is a program that aims to harness that process to build a fusion energy plant, first of a kind, that will enable us to deliver power to the grid using that power that powers the sun and the stars. My name's Jonathan Keep. I've been working for the last 10 years to develop an architecture that could be a commercial pathway for fusion energy that will deliver energy for us for the future. What I'm going to talk to you today about is about how this program works, what are we trying to deliver, but also how much information and data we need to generate and how many different people need to collaborate and work together to enable us to deliver this amazing progress for humanity. What we need to do is we need to capture all of this knowledge and science, and we need to share it with a wide range of suppliers. And what we're doing is we're building our platform to do that on the 3DEXPERIENCE tool. I'm going to talk about both the program and what that is. I'm going to talk about the vision for the platform that we're building, and then where we are currently on our journey. To start with, and it seems to be a bit of a trend, I'm going to start with a little bit of science. So we've gone from bees to gators. Now we're going to go into something, a bit of particle physics. So, you know, just a bit light for the morning. Right, so fusion itself is the process that powers the stars and suns. What we take is hydrogen nuclei, and they merge together and they produce this energy for us. On Earth, we can use a mix of forms of hydrogen, deuterium and tritium, and we can put that together in a machine to cause fusion to happen. Now, the sun has a big advantage over us. It's enormous. It's got lots of density. So the particles have lots of time to bump into each other and have these fusion reactions. And in fact, it's really useful that that process takes quite a bit of time in the stars, because if it was as quick as we're trying to do on Earth, we wouldn't actually exist because the star would have burnt out long ago. What we need to do to replicate the same conditions is we need to heat that gas up to 10 times the temperature of the sun. So we get to 150 million degrees. And that enables the conditions for fusion to happen. Now, what's interesting about this is that the amount of fuel that we need is very small. Relatively speaking, we have 1 gram of fuel producing 340,000 megajoules of energy. Now to put that into context, that 1 gram is equivalent to 14 tons of coal. So the UK Atomic Energy Authority has been working on fusion for a number of years. The mission has been to lead the delivery of sustainable fusion. and actually try and get to the point where we can get an economic benefit from all of that research and development. To deliver that benefit, STEP has been chosen as a pathway to actually generating commercial fusion. So we create a prototype that demonstrates the viability of the technology and gets us towards a point where we can actually deliver fusion power plants for everyone. It's a pioneering, first-of-a-kind program. What we're developing has never been done on Earth by any human. What we have to do is we have to be brave, we have to take some risks, and we have to understand that, embrace the uncertainties that surround us. It's a massive program where we're trying to bring together the best of science and many novel technological developments to engineer something for the future. As a first of a kind, it combines many different challenges. It has the complexity of integration that you would see in an aircraft, where many systems are interrelated. You have to trade between different requirements and different balances that mean you have to compromise, and you have to understand how to create the best compromise between all of these requirements. It's a power plant, so it's going to be big. The size of the site is going to be equivalent to the size of the Olympic Park in London. It's going to be a massive site. So you've got that complexity, but it's on a sizable site. It's not just on an aircraft size thing. We're talking massive scale. And then finally, we've got uncertainty. Absolutely huge levels of uncertainty. Equivalent in uncertainty to the same that was there in the 60s when NASA set off on the path to the moonshot. And actually, that's great. It gives us lots of stimulation for trying to develop the program. The opportunities are remarkable because there are so many new technologies. And this leads us to what we're trying to deliver. And it's not just about delivering that power plant. When we deliver the power plant, we will build and generate a load of data and information that will get stored in the 3DEXPERIENCE platform. But actually, by generating all that data and by looking after it and capturing it in a means that is accessible to everyone, that enables us to do much more. Firstly, with the plant itself, not only can we demonstrate that we've got power and we're able to deliver power to the grid, we can also then do further advanced developments. We become a facility for future developments, enabling us to enhance the performance of fusion for the commercial plants going forward. As well as that, what we will have built is an industry. To supply all of those components, to understand all these technologies, we will have to have developed suppliers and an entire supply chain that enables us to deliver this. And that is the real value. Not only do we get a demonstration fusion plant, but we also have all of the building blocks and the capability to deliver those. And even if the exact power plant that ends up being the commercial future, having understood each of those building blocks, then no matter what concept, what direction we go in, we have the capability to deliver in the future. As a program, we've selected a site. Our site is going to be in West Burton, in North Nottingham, in the UK. This is a site which has a long history of power generation. It's part of what is affectionately known as the Megawatt Valley, where along the River Trent, there are a number of coal-fired power plants that are all coming to the end of their life. They're being decommissioned. The plant at West Burton is shut down last year and is currently in the process of being decommissioned. The area surrounding there is struggling because of the loss of all of those jobs and the loss of those power plants. And what STEP is offering is a pathway to a new future, a brighter future, still within energy generation, which the area and region has a proud history of, but looking towards the future source of power. So then we have a timeline. So this is the interesting part for me, in the fact that the timeline is very long. Previous to working in Fusion, I worked in motor racing, and the timelines were incredibly short. They wouldn't even feature on this sort of timescale for a product. We're looking at building towards setting up our first operation in the 2040s. There are big chunks of work that are loosely labeled together, and now, like all of these plans, they're kind of idealized. They don't real engineering doesn't quite work like this and fit into neat packets. What we're going to have is a load of work in a conceptual space that will sort of bleed into that more detailed design as we understand and get better definition. And at some point, we start converting from design into manufacturing and construction, and eventually we get to operations. The other part of it is how we deliver this. So the program is UK government funded. Our sponsor is the Department of Energy Security and Net Zero, and that provides a lot of guidance and drive for us. We are set up as a limited company. UK Industrial Fusions was set up specifically as a vehicle to deliver the STEP program. The reason for this is because it's aimed to be a public-private venture. So not only is it using government funding, but is also then in partnership with a range of private companies who will enable us to deliver. UK AEA has a strong research history and has a great understanding of the fusion process and all of the building blocks that we need to enable fusion. However, it doesn't really have the capability to deliver a massive program like this. And so what we're reliant on is engineering partners and construction partners to allow us to build and develop this plant. So what we need to do is we need to collaborate with all of those different companies, and we need to enable those people to access the understanding and knowledge that has been developed within UK AEA. And this leads us neatly into our plant information management system. This is a system that we've developed and named because what we need to do is bring together all sorts of different data and information. We have an inordinate number of bespoke analyses and tools that are developed to allow us to understand the behavior of the plasma in the heart of the machine. But what we want to do is we want to bring bring all of that science and knowledge together and develop that together with the engineering side of things. And so PIMS is the hub that brings this all together and is built on the 3DEXPERIENCE platform. So if we go back to the mission in the first place, the two main things we're focusing on is firstly, the delivery of our prototype power plant. And then secondly, about how do we generate that industry. And as I just described, PIMS is that hub of our knowledge. It enables us to model the system behaviors and to understand the requirements, but also then enables us to capture all the data that we're generating in doing the design and provides us with that management intelligence and enables us to communicate widely across the teams. We're currently in this phase. We're trying to understand what exactly are we trying to design. The problem of fusion is that a fusion power plant is a knotty problem. It is a twisted, tangled web of all sorts of interrelated systems. And through model-based system engineering, we're trying to decode that, create and understand individual systems that have really strong definition of what they need to do, what they need to deliver, what behaviors they need to do, what functions they need to deliver. Having done that, we then get the opportunity to work more collaboratively with people without necessarily full expertise in the whole fusion, in the fusion world. They will have clear specifications for components or systems that are easier to understand. And they can then go on and start designing and developing those systems within that platform, using the tools and power within the 3DEXPERIENCE platform to both develop the design themselves, but also collaborate more broadly across all the partnerships, all the partners within our integrated team. And having worked out what exactly we want to develop, we then have to work out how. How are we going to deliver this? How do we manufacture these components? When do the components need to arrive? How do we build this together into a working facility? And in parallel, we need to complete and start construction of the site. And so what we've got is complex engineering as well as a large site, a massive construction program to build and develop for the future, for the plant. Using the tool set within 3DEXPERIENCE and the management intelligence that we can gather through that build, we're able to monitor progress, and the vision is that we can then manage delivery times and how construction is going, and then managing that commissioning of different facilities as they come online, using the tool to give us the understanding of progress and to enable us to monitor and manage the delivery. And finally, we get a power plant. We get our fusion machine, and we get it up and running. And at that point, we have our twin. We've had models and simulations that will have been running for years and years that have been giving us predictions of how this might behave. And at this point, when the machine switches on, we truly have a twin. Until we've got that real-life physical entity, we've just got simulations and predictions. And now we're able to validate those. We can use those simulations and predictions to try and optimize the performance and improve the behavior of that machine. We can also monitor the system. We can understand how certain components are degrading, manage their performance and lifetime. And we can use that condition monitoring aspect to drive us to understand how the performance is going over time and look at what proactive maintenance we may need to do for key systems. And assuming all that works, and it's all great, we have the next step, which is saying, well, we've built up all that knowledge. We have a machine. We understand how it is. We've got a blueprint that we can now use to develop a commercial plant, and we can ship that. Technically, it can go all over the world, wherever we feel that we're able to deliver this as a product. That commercial pathway may not be exactly the same as the design that we build in the 2040s, but it will be built on the foundations that we've developed through that process. And in the end, the sad part of it is that it will still have a life. There will be a point where we, too, will have to decommission the plant that will have been built on the West Burton site. And all of that knowledge and information that we've developed and built up over time makes that job so much easier. Many of the challenges with decommissioning are the challenges of archived data, of not knowing what exactly did you have, what was there, having to rummage through libraries of files and documents that were made 20 years ago, and you're not really sure what is really there. That creates all sorts of problems and all sorts of issues for engineers in the future. And what we're aiming to do is to have a much better legacy, to enable us to actually allow for those engineers of the future that are likely going to be younger than my children now. Many of the people that will be doing this decommissioning, they're probably not even born yet. And so what we've got to do is create that data legacy that enables them to follow that path so that they can perform the decommissioning safely and effectively when the plant finishes. So that's all about the vision that we've got for our plant information management system. But what really interesting is, where are we today? So as Aston pointed out, we've been working for the last couple of years, And we're currently building and implementing the PLM system and building our data set around that. We're building those foundations that enable us to build this massive data model. As we highlighted earlier, we're based on a systems approach. We have systems at the core of our data model. So what we want to do is use that model-based approach to understand the functionality of all those systems and to enable us to decode this very complex problem into a problem that's manageable and shareable across a wide team. The work at the moment on the systems is about creating models. So we've created system models to analyze the functions that we require for the plant, and we're currently decomposing that into the systems at each of the levels below that to enable us to write those requirements and derive those requirements with confidence, create that robust basis for design to be built on. In parallel, we are still developing design. We're exploring the feasibility of the requirements that we're writing. We're understanding what that reference design might look like and whether that even looks like it's going to work. We have to manage the data that we're generating, manage those baselines so that people have a common source of truth. That we don't have hundreds of people all working on their own different submodel of the plant. There is one core model, and that enables people to work collaboratively and to understand the progress and development that we're making. And last of all, we need some management intelligence. We need to be able to understand what's going on. So the slide shows our risk management and how we may look at where our risks are and what are the major risk areas, which is one aspect of helping us plan and direct the focus of what we're doing. But we're also looking to implement targets based on the maturity of the design, what level of definition, what level of confidence we have in the systems that we're delivering. And by understanding where we are now, baselining that within the system, and then creating targets for the future, that enables us to drive and prioritize the design work. So that's where we are now. We've now got I'm now going to talk a little bit about our next steps and the next challenges. The first part links very strongly with the Share PLM talk that was just given. The key challenge for us at the moment is that implementation and adoption. So it's great. We've got all these capabilities. We've stood up our PLM system, and it's operational. People using it, not so good, because actually, that user experience at the front end is actually really critical. And if that user experience is a bit jarring, and those people are quite comfortable, they've done all their stuff before, they know how to work, they're going to go, yeah, that looks great, but I'm just going to carry on working as I always was, because that's what I like. So making that user experience kind, making it a gentle slope up into getting them to change their working practices, to make use of the tool, that's really vital. More than just training them in the tool and then going, there you go, you've got it. Actually, that culture and that behavior is important. We have a range of different people in our teams. We will have early adopters that will be keen. There'll be those champions for change that will be enthusiastic in learning this new tool and developing their work practices. And what you need to do is use those to help bring along everyone else. They can help catalyze that change in practice and behavior and maybe define new ways of working that we can adapt and move on with. There will always be some late adopters. There will be always those people who will refuse to give up their spreadsheet or their bespoke piece of Python code that they've developed over the years that they're not going to let go of. But what we need to do is work out how do we engage with those, how do we get the best out of them and still get them to do some of their work and deliver within the platform. The other aspect is about collaboration. I talked about setting up engineering partners and construction partnerships. We're currently in procurement for these. And these are major programs, major contracts that we're in negotiation with at the moment. That collaboration, we need to be able to do this through the tool. We need those partners to be able to engage with us and work with us seamlessly. What we don't want to be doing is creating a load of friction through data management and data handover, which just slows down any of our work and makes it very difficult to collaborate between multiple organizations. The partners that we're working with, it's not an individual organization. It's a collaboration of several organizations for each of those partnerships. So not only do we have the collaboration between us and our partner, but each of those partners is a partnership in its own right. And so we need to make sure that collaboration is as seamless and as easy as possible. So I'll come to my closing point. I'm going to highlight what I've just been talking to you about. And the first thing is obviously we are a huge, major program to deliver a first-of-a-kind prototype fusion energy plant. At the heart of our plant information management system, PIMS, is 3DEXPERIENCE. It provides that hub for us to bring all of the different data sets that we have across our program into one central location and enables us to collaborate seamlessly with people. We're building those digital foundations that enable us to deliver both the physical step and create a virtual step that we can manage throughout the life cycle of the plant. We're developing some great tools and processes, but what we've got to do is we've also got to remember the people. The culture of the people and that user experience can't be forgotten along that journey. Thank you very much for your patience.
Well done. Thank you very much. Well done.
Jonathan, thank you so much, because I think this is actually an enormous representation of what Stefan and Morgan spoke about earlier, which is that nexus of science, data science, and collaboration, all inside of a platform environment. And what you are doing is absolutely incredible. So it's impressive to see, and we look forward to checking in on this. We do have a few seconds before we leave for a quick break. If anybody has any questions for Jonathan, I know he covered a lot. Oh, we do have a few questions. And so we've got a microphone that is going to be coming around the room that will find its way to you. I did, as the microphone is coming around, I wanted to mention that I recalled as you were speaking from back when I was in physics, where they were talking about the equation of E equals mc squared, and how if you're able to perfectly extract that energy, what kind of a ratio you could do from an item to the power that it created. And it was, the example given is that you could take a grape, and if you extract all that energy, you could power the city of New York for an entire day. And so I would imagine you're moving in that same bounds, but the complexity is much greater, much, much greater.
Yeah, I mean, the energy that's stored within those particles is phenomenal, but releasing it is very hard, and that's the challenge. And we have fission plants that already are delivering against this. This is another way of delivering that power.
Yeah, of course. I think we had a question in the back of the room, please.
Hi, hopefully I'm audible. I'm Sachin from Amgen. I'm a product manager responsible for PLM implementation at Amgen, so I can definitely relate to the pains that you have talked about here today. I have two questions. The first is, you talked about don't just put your users into the platform, just expect them to work, right? Support them. What kind of organizational structure have you set up or have you identified that will allow you to provide that kind of support?
Okay, so initially, I'm going to be very honest here. So initially, we were almost over-focused on how all the different capabilities we wanted. And what we struggled with was actually saying, well, what you actually need is, what does the whole look like? What's that look like? And when we delivered those capabilities, and we had these capabilities coming online at the back end of last year, when you looked into it, it was a mess, because no one had really taken the time to try and say, what does that look like? And what we recognized was we needed to do something about them. We need to own that whole vision, not just worry about the individual functionalities. And so that for us has been the key part, is to try and take ownership of what does that integrated whole look like? What are we actually trying to deliver there? And that's the main thing I think that we've learned recently, and we're setting up a structure around managing that.
So I think it's fair to say as well that there was a massive concentration about deploying capability. UK IFS is a new organization that hasn't had that legacy of decades and decades of PLM tools. It was really, okay, let's get these tools in and ready. And then we kind of recognized, actually, there is such that huge people and transformation. I mentioned at the start that it's not really isn't just a software deployment program. This is absolutely a fundamental.
It's quite transformational.
Hugely transformational across an entire organization.
Right.
It does sound like you're applying systems thinking and engineering to your implementation, right? My second question is around your partners. You mentioned that you're bringing them into PIMS. I'm curious because most of those partners either have their own PLM experience and their own systems, they have their own ways of working. What kind of either compliance or resistance have you found in getting those partners into your PIMS system?
So I'm gonna be a little bit coy about this, partly because at the moment we are in dialogue with partners that are bidding against the tender. So I can't really comment exactly how we're setting that boundary. The vision is for them to be working and providing within the platform. Exactly where that line is drawn between handover to their own systems and our systems, that's part of the process, that's part of our negotiation. One of the things we're being realistic about is that at some point in that supply chain, it doesn't matter whether it's with our immediate partners or with maybe suppliers or suppliers of suppliers, somewhere along the line, there will be a boundary where you go outside of that system. And what we need to do is understand how do we deal with that handover as efficiently as we can so that we don't have that friction that often ends up happening when you're trying to hand data between different systems. And that's not only a source for slowing down response, but also a source for error and concern. So what we need to do is work out how do we manage those transitions.
I think as well, there's a bit of often it's been a push out from the owner-operator to do that, but we've spoken to a lot of the supply chain and they've said, actually, we want to be working in a much more integrated method. They've seen the challenges of delivering major capital projects, turn up to site and realize that they're actually 4 weeks behind. You can't take this part from me. So they actually really want to get involved so they can deliver quickly, much quicker for the program so that ultimately we can get to the final part.
Very nice. I think we did have one more question. Matt?
Gentleman down here, yeah.
While the microphone is coming over here, I will let you all know, because we're going to be leaving for break in a second, there is a demo station on capital project execution. And so if you'd like to get into some more of these fundamental details, great opportunity to do this outside in the playground. Sir?
My name is Matthew Rogers. Thanks for the presentation. You mentioned that once you've got your prototype up and running, there's a desire to scale this globally. How many plants would be necessary to satisfy the demand of whatever energy mix Fusion's trying to target?
nice easy one to end on there.
So the plant that we're developing at the moment, the target is 100 megawatts. Now that's quite small relative to big power plants. So a conventional power plants, they're in the sort of 1 to 3 gigawatt sort of range. The challenge we've got is the uncertainty in the physics for us. So the target is not very ambitious relative to what we could get. But what we're wary of is if we kind of project that we're going to make loads of power, but it's reliant on quite a lot of uncertain physics and some aspects that we really do not have any precedent on, then we don't want to make a false claim. What we want to do is set a target we definitely can achieve that then has a route to go forward. So our aim would be in the same sort of category, in the sort of gigawatt category as a conventional power plant. Some of the novelty around our design is that it can run sustained. So some of the other tokamak designs, the challenge they have is they have to run as a pulse. So they can only run for a period and then stop and then have to restart. The design that we've got is based on physics that enables us to run for a sustained time. So the idea will be that then that can be much more of a base load and be kind of load following for a power plant operation point of view, and therefore be more useful to the grid in terms of being able to provide that base load in a more consistent basis than maybe, say, renewables can.
It's the same answer across all kind of power generation. It's not the answer, it's one of the answers that are going to support it as well.
Yeah.
Well, obviously, an incredibly important topic and also very cool as well. It helps us all nerd out on these types of things. So, Jonathan, Aston, thank you so much for the presentation. Really appreciate your time today.
Cheers. Thank you.